Chapter 6C, chi-squared tests. We're going to look at models with more than two proportions. So we're going to see how we can compare if there's a difference between three or more proportions. And we're going to learn three new ways of thinking about hypothesis tests. So take a minute and read through our why and learning objectives and the vocabulary. These three new hypothesis tests are the goodness of fit test, the test of independence, and the test of homogeneity. And the examples here really clearly illustrate the difference. Chi-square test uses the Greek letter chi here. So we read it like the chi in kite, but it's spelled like chi. And then the chi-square is read as chi-squared. The test statistic that we'll be calculating is the difference between what we observe and what we expected. We square it to make it positive because we like working with positive numbers in statistics. Then we divide by what we expected, and then we add it all up. Remember, this sigma symbol means that we add it all up, we sum. So if the sample distribution, what we observe, is a match for what we expected, this difference is 0. So we say that's when the sample distribution matches a null distribution exactly, and we get a chi-square value of 0. So let's think about how we would test if a die is fair. A gambler's accused of using a loaded die, but he says he's innocent. So we can think about each throw as one of 6 categories, right? Because there's 6 different faces. So in scenarios with more than 2 categories, this is when statisticians use the chi-square test rather than a z-test. So a z-test would be appropriate for a question about the average roll from a die, but not a question comparing 2 categories or 6 categories, anything more than 2 categories. So here's a record of the last 60 throws of this die that we think may be unfair. So if the gambler is innocent, how many times do we expect each number to turn up? So the fair proportion is p equals 1 out of 6 for each face. N is 60 rolls here. So the expected value, n times p, 60 times 1, 6, is 10 times each die face. Now we know there's going to be some variability due to sampling. So we don't expect it to be perfectly 10, but we don't expect it to be significantly far from 10 for any of these die faces. So count up these values here. You can see I counted 1, 2, 3, 4 ones. It's easy to go through and cross them off as you count with your pen, and fill in the observed frequency values here in your table. Check to make sure your totals add up to 60. And then let's just do a quick eyeball fit. How does what we observed compare to what we expected? The 1s look a little low and the 2s look a little low. The 3s look a little high and the 4s look a little high. The 5s and 6s are low, but maybe that's close enough to 10 that we're not surprised by that difference. So we said from an eyeball estimate, it does seem that 3 and 4 come up too often. 3 plus 4 is 7, so this may be advantageous to the gambler, right? A lot of gambling games pay out for 7s. So we can't draw any conclusions yet, right? Since there are many lines in the table, there's a high probability that at least one of them will look suspicious, even if the die is fair. So what the chi-square statistic does is combine all the differences for each of the 6 lines in the table by measuring how far the frequency of each face is from 10, which is what we expect, our expected value. So here's how we worked through the formula. Remember, the 1 came up 4 times. So we say, what's the difference? 4 minus 10. That will be a negative 6, so we square it to get a positive result. So that turns into a 36 divided by 10. We're squaring because we overall care about how far away things are, not whether or not they're positive or negative. If we have both positives and negatives, we may get 2 points that are both far away, canceling each other out. But we want to count the fact that those 2 values are both pretty far away, even if one's on the negative side and one's on the positive side. So by squaring and making all values positive, we're counting for those far out distances. So then the 2 came up 6 times, so 6 minus 10. We square that, we divide by 10. So you can double check all these calculations. You should get 142 over 10 or 14.2. So when the observed frequency is far from what we expect, right, there's some difference in here, we're going to get a large sum over here. When the observed frequency is close to what we expected, we're going to get a small sum. So we say large values of chi-square indicate that observed and expected frequencies are far apart. Small values of chi-square mean the opposite. Observed values are close to what we expected. So to find out if the chi-square statistic of 14.2 is reasonable, we need to know the chance of getting a chi-squared statistic of 14.2 or more. So from either a calculator, a computer, or a chi-square table, we would be able to see that for this chi-square value, for 6 lines in our table, we get a p-value of 0.014 or a 1.4% chance for a fair die to produce this chi-square value. So our p-value conclusions are still going to be the same way. And I'll show you on the next page how we can use a chi-square table, and I'll show you how we can use StatCrunch to find these p-values. So just looking at the p-value right now, what can we conclude? So this p-value is less than alpha's 0.05 significance level. So these results seem unusual if the die is fair, so we can conclude that the gambler is guilty of cheating. So in general, here's the shape of the chi-square graph. And like the T model, it changes depending on how much data you're working with. So a chi-square graph with 6 lines, like the 6 die, is centered here with the peak at 1 out of 6, or 0.16666 with the bars over it. See the peak here is a little bit above 0.15, so that's where that 1.6 is coming from. Similarly, if we had a chi-square graph with 11 values, it would shift over and start to look a little less skewed and a little shorter, and its peak here is at 1 out of 11, 0.0909. So we say this graph that had 6 lines has 5 degrees of freedom. This df is the number of lines minus 1. Similarly, the chi-square model that has 11 values has 10 degrees of freedom. So the degrees of freedom is always the number of values in chi-squared minus 1. The way of thinking about that is that if you knew 5 of those values in the table and you knew that the table had to add up to 60, you could work backwards and find that missing value. So as long as we know 1 less than all of the values, we can always find that remaining value. So that's why we say this has 5 degrees of freedom if there's 6 lines in the table. If you know 5 of those lines, you can come back and find that missing value. So 5 of those have to be independent. So in this gambler's example, there are 6 minus 1 or 5 degrees of freedom. So here's how we use a chi-square table. So similar to the Z table, before calculators and computers, students and statistics carried around books with these tables. So we have 5 degrees of freedom because we have 6 lines in our table. So we come over here and find 5 degrees of freedom. And then we look down the row to see where did our chi-square value of 14.2 fit in. So we keep going, keep going, keep going. Our chi-square value of 14.2 is between 11.07, which is 5% significance, and 15.09, which is 1% significance. So from the table, we'd say, okay, our chi-squared is statistically significant because it's less than the 0.05 significance level. If we were over here, we'd say, oh, this could be a reasonable difference. So here are some examples of research questions that the chi-squared hypothesis test can address. So take a minute and pause the video and read through these. You'll see we do what we call a goodness of fit test to see if the distribution of a categorical variable fits another set of data or if it's equally distributed. A test of independence is when we're looking to see are 2 categorical variables independent or not. And a test of homogeneity is to check if the distributions are the same across several populations or not. So in the vocabulary for the test of homogeneity, we gave the example of the 3 different NCAA divisions, right? Those would be 3 different populations, and we would check to see if steroids is different and the 3 divisions are the same. So example 2, we're going to look at a chi-square test for the goodness of fit test. So if births were uniformly distributed across the week, we'd expect about 1/7 of all births to occur each day. So here is data of births in New Jersey from 2003 for the whole year. There's less people in New Jersey than California, so the total is much less than the California total would be. And so eyeballing it, it looks like maybe these aren't evenly distributed, but we don't know could this have happened by chance or not. So we're going to investigate if they're unusual. So in StatCrunch, you can look for the file called Number of Births in New Jersey 2003 or type it in. I took the total, 116,823, and I divided that by 7 days to get the expected frequency here. So if everything were even, that would be what we expect. So here's this data in StatCrunch. You can see I've got my observed births, and then what I expect of everything is equal. So now we are going to do the goodness of fit test. So we go to Stat, goodness of fit test, and then we're going to choose the chi-square test. The normality test you would see maybe in an advanced statistics class, but for our class we just look at chi-squared. And then my observed values are in the column I titled Observed 2003 New Jersey Births, and my expected values are in the column I titled Expected Frequencies. And then I'm going to hit Compute, and what they've given me here is a chi-square value, which looks pretty large, and the p-value, which looks pretty small. So what does this mean? So if births were in fact distributed uniformly across the 7 days of the week, an observed chi-square value of 3,679.867 would occur about 0% of the time, right? Super small values there. This result is certainly unusual, so we reject the null hypothesis and conclude that the sample data are consistent with births being not the same or not uniformly distributed across the 7 days of the week. So here's the format for the formal hypothesis test. Notice for the alternative hypothesis, I put H1 here. You can also call it HA like we've been calling it. I think I mentioned earlier in the semester that people sometimes use a 1 here, so I just forgot to change it to an HA when I was typing. So the claim is that births are evenly distributed across the 7 days of the week. So we let P1 equal P2 equal P2 all the way up through P7, right? So in this case, that's the null hypothesis that they would be evenly distributed because the null hypothesis always has equality here. The alternative hypothesis is that the births are not evenly distributed, right? There's some difference. So we want to conduct a chi-square goodness of fit test with a significance level of alpha is 0.05. So we are rejecting the null hypothesis because our p-value is near 0, and that's less than 0.05. So what's our conclusion? There is sufficient evidence to warrant rejection of the claim that births are evenly distributed across the 7 days of the week. So in this case, when they talk about claim, they're corresponding that with the null hypothesis, right? As a scientist, you could make your claim either way. Most often, we think about the claim as associated with the alternative hypothesis, but here it's no problem that they have defined the claim as equality among all 7 days. So notice in our results, we record our chi-square value. We put down the degrees of freedom, which is 6 in this case, right? Because there was 7 days of the week, and 7 minus 1 is 6. And then our p-value here is so small, we said approximately 0. So now let's look at example 3, jurors in Alameda County. So this came from a study of grand juries in Alameda County in the 1970s, I think. They found that jurors did not seem representative of the population, so they did some studies. So note that we started age 18 because only people age 18 and over are considered for jury duty, right? So here is the ages broken into categories, and then here's the percentage of those categories that live in Alameda County. Over here's the number of jurors from a pool of 66 jurors selected at random, supposedly. So we can check, well, what would the sample proportion be? So group 1, our P1 hat would be 5 out of 66. You could see group 2, P2 hat would be 9 out of 66, and so on. And so StatCrunch does all those calculations for us. So our hypothesis, our null hypothesis could say the proportion of jurors is equal to the countywide percentages for each age group. Or we could say, all right, P1 should equal 0.42, right, because that's 42%. P2 should equal 0.23. P3 should equal 0.16, and P4 should equal 0.19. Then our alternative hypothesis we say at least one of the proportion groups does not match the countywide percentages, right? It doesn't have to be that they're all different. It has to be at least one is significantly different. So we're going to go into StatCrunch. And if you go to Jurors in Alameda County file, we've got our values in here. And we're going to do the goodness of fit test. So think about what is the expected value and what is the observed value. So the observed value is the actual number of jurors that were in this trial or in the random selection. And then the expected is the countywide percentage, right? So if we look here, our chi-square value is 61.26, and we had 4 rows in our table. Our degrees of freedom are 3, and so this is considered to be a small p-value. So we reject the null hypothesis because our p-value is very small. It's less than the 0.05. So for our conclusion, we say there is sufficient evidence that at least one proportion does not match the countywide percentage. It appears the jury was not selected randomly. If the jury were selected randomly from Alameda County, results like this would be very unusual. Okay, so let's look now at example 4, what we call a test for independence about animal testing. So we use the test for independence to determine if there's a relationship between two categorical variables in the population, right? Just like earlier when we looked at two-way tables, we thought about, is there an independent relationship between two categories like men and women? So take a minute and make sure you pause and read through this. The two-way table here is telling us the responses for males to this survey about using animals for medical testing, if it might save human lives, and the responses from females. So we want to know here, is gender independent of people's opinions about animals for medical testing, or is there some dependent relationship between being female or male and how you respond to this survey? So there's one way we could write the hypothesis here. We could say the null hypothesis is that there is no relationship between gender and opinions about using animals for medical testing. And the alternative hypothesis could say there is a relationship between gender and opinions about using animals for medical testing. Another way we could say it is the null hypothesis could say gender and opinions about using animals for medical testing are independent in the population of U.S. adults. And the alternative could say gender and opinions about using animals for medical testing are dependent, right? There is some relationship. And remember, we're always trying to write our hypotheses in terms of the whole population. So in this case, we're saying our population is U.S. adults based on the random sample from this survey. So we have to stop and think about, well, what's the explanatory variable? So we think that gender explains opinion, right? How people respond to the survey. So we say gender is the explanatory variable and opinion is the response variable. So that means when we do our calculations, we're conditioning on whether the person is male or female. So since there were 516 total males in the survey, we set up our conditional percentages as the number in each category divided by the total males. Similarly, for females, we use the total 636. I'm going to convert these to decimals just so it's easier to compare. You could certainly leave them as fractions. Check to make sure, give or take rounding, that your column totals are 1 or 100%. So just eyeballing this, does it seem like there's a difference or not? It's a little hard to tell in the table, but it does seem that males are more likely to strongly agree, right? Their percentages up here are much higher. And it does seem like females are more likely to strongly agree or disagree when we compare those back to the male percentages. So it does look like there might be a difference. So let's go into StatCrunch, and you can type the data or find the data animal testing for chi-square. So we're going to select stat and then tables. And this is a contingency table, and we're going to select with summary. There's not an independence test in the same way that there's a goodness of fit test. And then we want our columns to be the male and the female columns. So hold Control or Command if you're on a Mac and highlight those. And then for the row labels, we're labeling those by the opinion in the survey. And then you want to click on the expected count display here so we can see what we'd expect if they were independent. And then click on chi-square test for independence for our hypothesis test. You can see there's all sorts of different formulas that StatCrunch can run. We're not going to construct a confidence interval. If you take an advanced statistics class, you would do that with this data. And then we can hit compute. And so what we're shown here is our data that we observed, and then in parentheses, we get what we would expect if both groups were equal. So you could double check, 60.47 out of 516 is a match proportion-wise for 74.53 out of 636. So what they've done is they've pooled all the data together and figured out, well, how many total strongly agree, and then figured out if everybody was that same proportion of 135 out of 1152, how many of the men would strongly agree, how many of the females would strongly agree. So looking at what we expected in parentheses, these look different than what we have in our actual observed data. Higher in some places, lower in others. And we see here our chi-square value is 47.54, and for 4 degrees of freedom, that's considered significant. Our p-value is very small. Remember, there's 4 degrees of freedom because there are 1, 2, 3, 4, 5 different lines in this table. So we record our evidence. Typically, we write down the chi-square value, the p-value, and the degrees of freedom, and then we state a conclusion. Our conclusion is that we reject the null hypothesis. There is sufficient evidence to conclude that opinion in the survey depends on gender. If the survey opinions were independent from gender, results like this would be very unusual. Example 5 is a test for homogeneity. So we're going to open the data file about educational attainment data. And let's go look at that data. So we see here we have the 4 regions in the US, and then people are classified, this is a random sample of whether they were not high school graduates, some college, associate's degree, bachelor's degree, or if they had an advanced degree. So we want to know, are the populations distributed the same in these 4 regions of the US, or is there some difference, right? So homogeneity means things are the same, so we're testing to see, are things the same or not? So here's one way we can state the hypothesis for a test of homogeneity. For the null hypothesis, we say the residents of the 4 US regions are homogeneous with respect to educational attainment. And for the alternative hypothesis, we say the residents of the 4 US regions are non-homogeneous with respect to educational attainment. You could also say it slightly differently, saying, are things the same? So you could say the null hypothesis as the proportion of educational attainment levels is the same for residents in each of the 4 US regions. And the alternative is the proportion of educational attainment levels is not the same for residents in each of the 4 US regions. So now we're going to go into StatCrunch, and we're going to do a chi-square test for independence again. So even though it's a homogeneity test, it's the same calculation as the test for independence. So we go through the same process as the prior example. So we go stat, tables, contingency table, and then we do it with summary. And then our columns we want to select are the not high school grad, some college, associate's degree. I need to make this a bit bigger so I can select everything. Okay, make sure you get everything selected either using Control or Command if you're on a PC or Mac. And then our row labels are going to be what region the people are in. And then we want to see the expected count in our table, and we're doing the same calculation as the test for independence. So we choose chi-square test for independence again. And compute. So in this table, we get what we expect in parentheses, and that comes from pooling all the data together. So they take all the totals and then figure out how things should look from the column totals and the row totals. And so there were 4 rows and 6 columns in this two-way table. So how do we figure out the degrees of freedom? Well, 4 minus 1 is 3, and 6 minus 1 is 5. So we take 3 independent rows and multiply that by 5 independent columns and say the degrees of freedom are 15. Now, StatCrunch will do this for you, so it's not anything you'll have to do on your own, but it's good to know where this comes from. So our chi-square value is 7, and our p-value is 0.946. So that's not statistically significant difference. So we record our chi-square value and our p-value and the degrees of freedom. And then we say we fail to reject the null hypothesis since the p-value is large. If the educational attainment rates are the same for each of the 4 regions in the U.S., results like this are not surprising. The data indicates no difference in educational attainment between the regions.